Can you travel through time? Well, the cop-out answer is, of course you can. You're traveling through time as I speak. I mean, right now it's a certain time, and right now it's a later time. But I know what you really mean. Can you travel through time to the future? Can you travel faster through time than everybody else is? So you get to say 100 years in the future for everyone else, when for you, only a few minutes or a few seconds have passed. Well, the surprising answer to that question is yes. Let's see why. What I'm referring to is something called Einstein's theory of special relativity. Now, don't let the big fancy name scare you. It is actually quite simple if you can wrap your head around this one thing, and that is that light travels the same speed in all reference frames. Light goes the same speed in all reference frames. Now, there's a special little thing here. It means inertial reference frames, but for our point of view, that just means your reference frame is going at a constant speed. So first, what do I mean by reference frame? Well, the first thing you have to see is that everything is relative. That's why it's called the special theory of relativity. So let me show you what I mean by this. Say you're standing out here on the ground, and passing by you comes this big train, all right? And let's say compared to you, person A, compared to you, this train is going, let's say, 10 miles an hour, all right? Now, your friend, or maybe he's not your friend, maybe you don't like him, but let's just say he's your friend, person B is on that train. So now, compared to you, person A, that train and everything on the train, including your friend, person B, is going 10 miles an hour compared to you. Now, if that person on the train has a ball in his hand, or her hand, or their hand, and they throw it forward. Now let's say this person on the train, right? They throw it forward at 10 miles an hour with respect to them. So note, with respect to person B, everything else on the train is just stationary, right? Because it's all going the same speed compared to you. So compared to him and everything else on the train, he throws his ball 10 miles per hour forward. All right. The question is, how fast is that ball moving from the reference frame of you, person A? Well, let's see. The train's already going 10 miles an hour with respect to you, and your friend is throwing a ball forward so that it's going 10 miles an hour with respect to the train, which is already going 10 miles an hour with respect to you. So with respect to you, that ball is moving at 20 miles an hour with respect to you. Okay, but who's right, you or your friend? Well, the answer is you both are, because you have different reference frames. With respect to you, that ball's going 20 miles an hour, and the train is going 10 miles an hour. But with respect to your friend, person B, that ball's only going 10 miles an hour, and the train is not moving, because it's right under his feet. All right. Now, the crazy thing is that Einstein thought. He said, hey, I know this all makes sense, but what if light acts differently? So say we have the same setup, train, person A, and person B, all right? Now, instead of throwing a ball forward, the person on the train shines a flashlight forward, all right? He shines light. Now, you might think that light just happens instantaneously, because if you turn on a light, boom, you see it immediately. But actually, light just travels very, 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 very fast. That's the scientific name for how fast it travels. Not really, but here we go. So say he's shining light forward. That light doesn't actually just instantaneously fill up the train or hit the other side. It takes time to get there, but it's just traveling extremely fast. Light travels at the speed of light, which we call c. Now I know speed starts with an S, but or speed of light is denoted by c. And that goes at 3 times 10 to the 8th meters per second. So let's see, that's 3 with 8 zeros. 4, 5, 6, 7, 8. So that's 300 million meters per second. So every second that goes by, those photons of light, a photon is just a little packet of light, has gone, look at this, 300 million meters. So that's very fast. But here's the crazy thing, right? Your friend shines light forward, all right? So with respect to him, that light is going at the speed of light. Now say that train is going 10 miles an hour with respect to you, all right? Now, from what we learned about the ball, we think that, let's see, compared to you, the train's already going 10 miles an hour. And with respect to the train, the light is going at the speed of light. So from your perspective, that light must be going at a speed of the speed of light plus 10 miles per hour, right? Wrong. This is what's so crazy. Einstein, against what everyone thought, said, what if the speed of light is the same? So whether you're in your reference frame or your friend's reference frame, light goes the same speed. Now, if you can believe that, then you can believe the rest of this traveling through time stuff, which is actually called time dilation. And if you don't believe it, you can look up some great experiments where they've actually shown that light does travel at the same speed, and they've shown that time dilation, which is a direct consequence, as I'm about to show, of the fact that light goes the same speed in all reference frames. And so if you show that, then you've shown both. Alright, so if we can assume this, then we can do our final thought experiment and show you how to travel into the future. One more time, we're going to have our big train, right? But in fact, this has got to be a really big train, alright? So I'm going to draw a lot on it. Now, again, there's you outside, person A, and there's this guy inside. Well, sure. He's inside and he's person B. Now, say person B fixes a mirror to the top of the train, alright? And let's put the mirror over here actually. Alright? Fixes a mirror to the top of the train. Now, from his point of view, right? Person B, say he has a flashlight, and now he points it straight up, alright? So what's the light going to do? It's going to go up, hit the mirror, and then come back down, right? Up, down, right? That's from his perspective. But what are you going to see from your perspective, right? You're going to see, since this train is moving across, as the light goes up, the train also moves forward. So you're going to see the light go like this. It's going to go up and over and then down. Now it's going over because it's moving. And you can try this. Get you and a friend and have the friend at first just throw a ball straight up and down. And then have the friend start running past you and throw the ball straight up and down. With respect to him, it's just going up and down. But with respect to you, you'll see it go like this. So, here's where things get crazy, alright? So, again, to recap, from the perspective of the train, we'll call that perspective B. The light just goes up and then down. But from your perspective, perspective A, the light goes up and over and down and over. So perspective B and perspective A. Alright, now there's only two things you need to know for this to work out mathematically. But before we even do that, let's just think about it qualitatively. Ready? So the speed of light's going the same in all reference frames. But check this out. For person B, the light went up and it went back down. Okay, that's a certain distance that the light had to travel. But for you, person A, the light went up and over and down and over. Now clearly, this distance here is a different length than this distance here, right? Let me color code this, right? So this red distance is longer than the black distance, right? And then it comes back down. So the path that the light travels from your perspective, A, when it goes up and down, it's actually traveling further than from person B's perspective, where it just goes up and down instead of up and over and down and over. But wait a second. We're saying that light travels at the same speed in all reference frames. So that means, okay, wait, it's going the same speed, but it has further to go? But yet, the light starts down here at the same time, they both go up, and then they hit the bottom at the same time. So what does that mean? That means, from your perspective, it actually took more time for the light to go up and down this red path, all right? Because it's still going the same speed, right? The light from his perspective, B, where it's going up and down, is going the same speed as the light that's going like this, because it goes the same speed in all reference frames on the red path, right? So since it's going the same speed, but it's had longer to go from your perspective, person A, that means that it took longer for it to happen, right? If you and your friend are both going the same speed in the car, but you have to go 2 cities over and he only has to go to that first city, it's going to take you longer to do it. So what is that crazy, what does this imply that's so crazy? It implies that from your perspective, person A, more time has passed and less time has passed for person B. Now if we ramp this up, that means person B, less time is passing. So if you and person B are the same age exactly, if you're twins, then if person B is going by you, he's actually getting younger than you are. Because look at this, more time is passing for you and less time is passing for him. So this is called time dilation. So person B is literally traveling through time with respect to you, person A. That just blows my mind. And let's make this mathematical. You only need to know 2 things, which is the definition of velocity and Pythagorean theorem. And from there, it's just a little bit of algebra. So, check this out. Painless velocity, or which is just speed with a direction, is distance d over time t. All right? That makes sense. When you're driving in your car, you're saying, I'm going really fast. How fast? 60 miles per hour. That's a distance over time. All right, and the last part is Pythagoras' theorem, where if you have 2 sides, length A and B, and the hypotenuse has length C, and this angle right here is a right angle that both A and B touch, then the length of A, the length of that side, A squared, plus the length of that side, B squared, equals C squared. Alright, so let's check this out. Ready? One more time, we have our big train, alright? Now, from A's perspective, remember A is stationary out here, watching the train go by. The light goes up, and then it comes back down, all while going over. And I'm actually going to make this red, sorry. A is in red, so we don't get confused, alright? And then B, let's make B blue. B the light just goes up and it comes back down. So that's from perspective B, the person on the train. All right, so let's do a little bit of math here. So if velocity is distance over time, then multiplying both sides by time, we see distance is velocity times time. So we can talk about these distances of a, what do we see here? A triangle, 6, so we can use Pythagoras' theorem. We can talk about these distance if we know velocity and time. All right, well, let's look at this one right here. I think this is the easiest. So what is this distance right here? Well, let's see. It's determined by how fast this train is moving, right? If there's like this end of the train is here, right? And with respect to person A in his reference frame, that end of the train is moving from here to here as the train moves across, right? Okay, so, and that depends on how fast it's moving. So let's say that the speed of the train is v, all right? So this distance is going to be that speed, v, times time. But now we just learned time is relative, so whose time are we talking about? Well, let's see. This end of the train is only going to move over with respect to the person A, right? With respect to person B, if he's standing right here, the end of the train is always going to be underneath him, because then he'll be over here, right? So from his perspective, the end of the train doesn't move. So we have to say it must be from person A's perspective where it's moving. So this distance must be v times time in the reference frame of person A. Now let's look at this guy right here. So this distance right here, I call distances guys sometimes, don't know why, but here we go. So this guy right here, let's see. What is traversing this path? Light. Okay, so the velocity here we're talking about is c, the speed of light. Remember? Right? Because light is going on this path. It's going up and over. And what time are we talking about? Well, in which reference frame does light take this red path? Person A's reference frame. So this is c times t in A's reference frame. Now let's look at this last distance here, all right? The blue distance. Again, light is traversing this path, so we're using c as the velocity. But in whose reference frame does light travel this path? In B's reference frame. So that means it's c times the time in B's reference frame. All right, hope that makes sense. And now we can do our last little bit of magic, right? We're going to do a squared plus b squared equals c squared. So a and b are these guys, right? The sides. Here's our right angle because we have a triangle, and this is c squared. So this squared plus this squared has to equal that squared. So let's see that. That's VTA squared plus CTB squared equals CTA squared. Let's just make sure we did that right. VTA plus CTB. Right. Now, let's simplify this. So we have V squared TA squared plus C squared TB squared equals C squared TA squared. All right, cool. Now, we want to relate TA to TB. So let's solve for TA, right? We want to see how the times change. So doing that, let's bring this over to the other side. So doing that, we get C squared TB squared equals C squared TA squared minus V squared TA squared, right? Now let's factor out this TA squared. So we can go like this. Minus V squared. And now, let's just divide both sides by c squared to get rid of this. So we're gonna divide by c squared. And then we can simplify this fraction because c squared over c squared is 1, and then this will be v squared over c squared. So this becomes Sorry, this becomes 1 because it's c squared over c squared, and right here becomes v squared over c squared. Now, usually what we like to do is then just take a square root of both sides. So take the square root of both sides and gets rid of the squares and puts a square root over this guy. Alright, here we go. Here we can relate TA to TB. Now scientists usually like to bring this factor over to the other side, so that's all we'll do, and I'll write it over here. TA is TB over the square root of 1 minus v squared over c squared. Or, bringing them both inside the square, v over c squared. Now we can really talk about what's going on here. So remember, TB is the person on the train, and TA is the person off the train. So let's see what this formula says. First of all, v is the velocity of person B with respect to person A. Remember, because person B is on the train that's going speed v with respect to person A. So if person B is not moving with respect to person A, then this v is 0, right? So that means this goes to 0, 1 minus 0 is 1, square root of 1 is 1, so the times are the same. Well, that's good. That means it all works out, because if they're not moving with respect to each other, they should have the same time. Now, what happens as person B starts moving faster and faster with respect to person A? Well, then this V gets closer and closer to C. Now I want you to note that C is also like the cosmic universal speed limit. Nothing can go faster than the speed of light. Trust me, you can try, but you just aren't going to get up there. And that'll be another video why you can't do that. That would be for another video. But just believe me, you can't go faster than the speed of light. So as this V approaches this C, right? As V gets closer and closer to C, this fraction goes from 0, gets closer and closer to 1, right? It's like 1 over C plus half C over C plus, like 3/4 C over C. So, it gets closer and closer to 1. So, that means that this number gets bigger and bigger, right? And so that means this number gets closer and closer to 0, because this number approaches 1, and this is 1 minus that. So if that gets close to 1, this gets close to 0, and it gets from the top, so this denominator gets smaller and smaller. So if you divide by a smaller and smaller number, the answer gets bigger and bigger. So that means the faster person B is moving with respect to person A, the more time has passed for person A than compared to person B, or the less time has passed for person B than for person A. So that means the faster person B goes with respect to person A, the less time passes for person B. So person B could get in a rocket ship and go really, really close to the speed of light, and when they return, more time has passed for person A and less time has passed for person B. When they come back, person B could only be, 1 year older, while person A could be like 100 years older. So you can literally travel forward in time faster than everybody else into the future. Now, why don't we notice this in our everyday lives? Well, that's because most of the time when we're moving compared to other things, we are going very, very, very slow compared to the speed of light. Remember, it all depends on this fraction here, V over C. And usually this is a really small fraction, so this is a really small number, and 1 minus a really small number is basically just 1. So TA is pretty close, practically the same to TB. So this would only occur if you got really close to the speed of light, which we just don't move. We just don't move that fast. But particles do, and so we can see those effects when we do experiments like that. And in fact, they've taken 2 atomic clocks with super accurate, set them to the same time, pretty much exactly, and kept one stationary and flew the other one around the Earth really quickly. And when they came back, their times were slightly different, proving time dilation and that Einstein was right the whole time. And so this doesn't happen in real life because we usually go a lot slower than the speed of light. For in fact, the speed of light in miles per hour is about 670 million miles per hour. When, in your car you're only going 60 miles per hour. So there's no way things are getting up to the speed of light. That's about 186,000 miles per second. That means you can calculate, that means light could go around the Earth 7.5 times in just 1 second. 7.5 times in 1 second. When compared to a jet aircraft going at about 500 miles per hour, it would take 4 hours just to get across the continental United States. 4 hours. And in 1 second, light would go all the way around the equator of the Earth. Not once, not twice, but 7.5 times. So, since we move so slow compared to the speed of light, we do not see the effects of time dilation in everyday life. But, seeing is not always believing, and now that you have seen this proof, you now know how to travel into the future. If only you can figure out how to go fast enough. Well, thanks everybody for watching. My name is Ben Hall, and I hope you've enjoyed this little physics lesson, and hope to see you next time. Bye.